Hey guys, how are you doing today? This is the first homework submission deadline. Um, so if you have any questions, but I, I don't think it was difficult. So the second homework, the deadline is next Monday, but we will extend this till Friday because we didn't cover um, recurrent neural networks that we will cover today, I hope, for sentence level classification. Okay, so let's continue our coding notebook. Um, hmm, voilà. Mhm. And I will upload the notebook from last time. Um, so I will upload this data set, run all the code until embeddings. Aha. So we stop on this make batch function. And uh, it returned the embeddings for title and description of the job and one hot encoder for other features. So now I want to talk about this modification of the max pooling. As you remember, we wanted to use max pooling um, to get the one vector from several embeddings. But their modification, like average pooling, soft max pooling, attentive pooling, that I want to talk about. And after that, um, yeah, but first let's just train a simple model and then talk about recurrent neural networks. Okay, here's the batch. So in batch, we have these numbers. For example, some numbers here. If you want to read um, back to reconstruct the sentence, um, we can do, okay, it provides the correct code, token ID for token I for I in mhm, like that. And if you want to get back the sentence from these numbers, you can just apply our uh, dictionary, and it will return by the index, which is the same as the token ID, the word. So it returns senior support worker pet. So um, okay. So this is how we converted the sentences into numbers. Then we talked about linear layer convolutional, 1D convolutional, and embeddings. And yeah, let's try to create a very simple model. So let's create a simple embedding layer. Create class. And for example, we will do full description or title. Oh, actually, it started to write the correct code. Title and code, but why it changes? Oh, okay. So yeah, this is just right the correct code. So in Torch, we inherit from a neural network module. So let's see if the rest of the code is correct. The dictionary is length of tokens, yes. The dictionary size. The output shape, okay, let's use 64, but if you will use pre-trained the embeddings, it will be 100, for example. Super init. Then we initialize embedding layer with these dimensions. And we don't need convolution. Um, do you remember what um, we want to do? We want after so after so embedding layer. Let's see for text. Yes, we create embeddings. Then we applied convolution, and then we apply the maybe non-linearity, and then we take the max pooling. So let's and the AI assist actually understands that we want to apply convolution layer. So what will be a hidden size? So hidden size is the number of input channels. In channels. The second number is the output channels. The number of output channels can be different, but let's keep the same for now. And 3 is the kernel size. So padding. If we want to get the same number of vectors on the output, then we should add padding. If we don't care, um, we can um, live without padding. So what else? Then we will also use, and you can use actually several layers of convolutions. So you can stack another convolution, but for now, um, I actually, what is that? Adaptive mass pooling. Um, Adaptive mass pool. Because I was thinking just to take the maximum on over all channels, but maybe there's a built-in function. Um, let's see. The input is the number of channels and length, and the output, hmm, length out. Okay. And what if we use as length out one? Maybe it will perform as max pooling actually. Um, okay, let's maybe ask because I was thinking just apply torch max, but maybe it's nicer way to apply max pooling. So let's ask ChatGPT. Can I use torch max pooling as a global max pooling? Yeah. Yeah, so if we indicate the output size as one, then it will perform as just max pooling. Okay, good to know. So, yeah, let's just use it. Um, I want to use the non-linearity. Mm, and this adaptive max pooling, and maybe just one convolution layer for now. Okay, so oh, it actually continues the code for me. So the next um, function that we should include in any NN module is forward, where we actually apply these layers to our input batch. So forward, uh, uh, forwards, and here I will just use X. So first, okay, the code is ready. So we apply embedding layer. Um, Embedding layer, let's see, we had some um, um, embedding layer has the vectors in rows. If we want, but convolution layer um, considers as length the last dimension. So we should transpose to change the um, last and upper last dimensions. And then we are good to apply convolution. After we apply convolution, we apply nonlinearity. Then you can apply another convolution layer. Um, and adaptive max pooling. In this case, it will work as global max pooling. Um, and hmm, I actually didn't know if we should use squeeze, but it seems correct. Let's try to apply this layer to our batch. So let's initialize this title encoder and apply some, so, yeah, and apply to this to this tensor, which is actually a batch of title. And let's look at the shape. Yeah, the shape is correct. So without squeeze, we would have extra dimension. This is how this adaptive pooling works, I think. So after squeeze, we have just one-dimensional vector. Actually, what we want from our encoder, from the it takes as input the embeddings, and the output is just one vector. So and now we can use this in our model. For example, okay, it provides the code. So we create this encoder here. Yeah, and what else? What should I use as a loss function for the salary prediction? Cross entropy or MSE loss? MSE, yes. MSE. For MSE loss, what is the dimension of the target? For cross entropy, the dimension is the number of classes. For MSE, we won't predict one number. It should be just one. So we should add a linear layer that will change the dimension of our encoder into one. So we also need a linear layer fully connected, so FC. Um, let's see. So the output features should be one, because this will be the prediction of our salary. So what is about here? Input features. let's see. In encoder layer, we should pass end tokens and hidden size. So the output shape here will be this hidden size. So end tokens will be the input to our encoder here, and tokens. And this hidden size, let's see. Aha, here it's 100, 100. I can change. Actually, we can keep 100. Okay, let's keep 100. So the hidden size will be 100, okay. And then the number of input features will be this hidden size. And number of output features will be 1. You can apply two linear layers, like from 100 to 50 and then from 50 to 1. But now, just to make a two example, I'm using this one. And we're done. So here in the forward, we just apply to our batch encoder. Oh, by the way, yes. So actually, this code is correct because the batch will be a dictionary, and this encoder will be applied only to title. In your full model, you will create also encoder for description, and you will pass also this from embedding, and then you will concatenate these two output vectors. But for now, we use just one embedding for title. And of course, prediction will be very poor with just one title information. So title embedding, and we apply fully connected to title embedding. Okay. And then the rest of the code is written for you. Just create the model. There are some assertions. And we didn't pass assertions because I didn't use the categorical features. And then there is train and loop. And yeah, it looks like it works. What is that using? It is different. Let's see. There's something that I didn't expect. Let's see, stop. Maybe we should also return the target in our forward. Oh, no. Okay. I think the problem is that it returns the batch times 1. Let's see if we use squeeze here. Okay, yeah. So we should, because our target is kind of zero-dimensional, so we should also remove one extra dimension in forward. And yeah, it's trained. So for homework and the use of GPU, I want to give you some advices. So some advice. So first, try to run your model on like in CPU mode, because you may run in some errors like I had in the previous um, step. When you run, for example, one epoch on CPU, and you think that accuracy that you will see uh, after the first epoch is pretty good, then you can go to runtime and change runtime to GPU. And after that, you will need to run all the code again because it will like finish your previous session, and it will work much, much faster. But after you reach the desired accuracy, which is 0.1, if I'm not mistaken, uh, then make sure that you disconnect your GPU. I believe it's here. Disconnect or manage sessions, because and try to use GPU no more than for 1 hour per day, because later on we will need GPUs for large language models, which we can't run without GPUs. It will be very slow. So save the time for next week's. And Google provides 3 hours, but after some threshold, it will actually stop providing access to GPUs. So just try to use them for the just amount of time that you need to train your model. But even if you will use your limit on this free GPU, maybe it will be renewed after 1 week. But for a week, you won't have access to GPUs. And I'm still waiting for reply from the computational powers. Oh, not actually not bad. we used we used just one title, and the prediction, the MSE in the prediction of log dollars is 0.2. So yes, but well, if you will want to use very large GPUs on Colab and have unlimited time, you can pay $10 per month, and you will have unlimited access to 40 gigabyte GPUs. Free GPUs are 16 gigabytes, but it will be enough for our needs. Okay, so I will stop training, and will provide one more remark about two embeddings for your final model. So we created, let's see. So we created the embedding layer last time. And if you create embedding, a different embedding layer for description, then you will need to store additional metrics of the size of dictionary times the length of embedding. why don't we use the same embeddings for words in both in title and description? Why don't we use the same word embeddings? So you can create the second embedding, like oh, let's create one embedding and the second embedding. And as you remember, these embeddings, they have the weights, the embeddings themselves. Embedding dot weight. And if you want to check embeddings of the first embedding and the second embedding, they will be different. So it creates two different matrices. But you can use the same embeddings. And how can you do this in code? You can just assign, for example, to the weights of the second encoder, the weights of the first encoder. And as you remember, in Torch, it works as links. So when you change any of these embeddings, the other embeddings also will be changed. It will save your memory and also the computational resources. And after that, when you, yep.
So we're using two embedding layers, like one in each class, but they're linked so they have the same weights, correct?
Yes,
Okay.
the same parameters.
Okay.
So, well, you can use different, but it's just a suggestion.
Okay.
to make the training faster. And after that, you will just concatenate, and you will get the vector with embedding of title and embedding of description. And then you apply linear layer. But also you will add the vector, which is one hot encoder of the categorical features. And this will be actually the final model. Pre-embeddings and concat. And of course, you will need to use maybe at least two linear layers in the end, because it will be too large layer to shrink just into one. So you will need to apply maybe two linear layers from this size to 200, 100, and then from this to 1. And don't forget non-linearities between these two linear layers. Okay, so now let's talk about other approaches, which are average. So for average, instead of taking the max, you can, yeah, and in your homework, I asked to implement two models, different models. So one model can be like this simple one, another can use, for example, one of different poolings, or it can be just recurrent neural network that we will talk about. So for average, you will just sum up all the output vectors from convolution. And to normalize, you should divide by the square root of the number of vectors. Not by n, but the square root of n. That will preserve the variance. You remember your question was, so if we divide by the square root of n, the variance will be so if we have the sum of random variables, and if we assume that they're independent, then it will be n times variance of one variable, n times variance of x1. So if we divide by the square root of n, the constant goes outside a squared constant. So it will be n, and n will cancel. So the next idea to use so-called softmax pooling, and the formula is here. You sum up these vectors h, like hidden vectors, but you also multiply by the weight, which is defined by softmax function. The most complicated is attentive pooling. So let's talk about this attention layer. So in the simplest case, you can use just arbitrary constants here that sum up to 1. So you will just take the you will sum the hidden vectors after convolution with some coefficients that sum up to 1. But we want actually to learn these coefficients. So how can you create this attention layer? There are many different ways. So the classical attention says that when you have vectors h1, h2, and so on, hn, you calculate these attention coefficients as follows. You take the dot product of h1 with h1, the dot product of h1 with h2, the dot product with all other vectors, h1 with hn, and the dot product of two vectors is just a number. So you will get some numbers here, like let's note this alpha1, alpha2, and so on, alpha n. But these numbers may not sum up to 1. So you will need to apply softmax to these numbers to get probabilities. So apply softmax. And after applying softmax, you will get actually normalized alpha1, alpha2, and alpha n that sum up to 1. And then you can take the this weighted sum. So it will be alpha1 times h1 plus alpha 2 times H2, and so on. So this is called attention function. And in my example, by attention function, I use the dot product. The other way, so then you do the same with H2. So this will give you kind of a new vector for H1. Then you do the same for H2. Then, so after this applying attention function to H1, you will get a new H1, which is a linear combination of all the vectors. Then you will get updated H2. So you will need to calculate the dot products between H2 and H1, H2 and H2, and so on. And so on. And after that, you apply max pooling. This is called attentive pooling. The other way that I prefer, so this is the classical attention. The other way to introduce a new linear layer. Let's see. I can show in my code maybe. Mm. Mhm. Because this is one. Um, no, 1 second. Oh, it's here. Attentive. So another way to implement this, just to create a linear layer and additional linear layer, and apply this linear layer to the there are different attentions. One is called additive attention, when you apply this to the sum of H1 with H1, H1 with H2, and so on. And there is also multiplicative attention when you apply linearly to the products, H1 with H1, H1 with H2, and so on. So here I used, I believe, the additive attention. Mhm. Um, well, maybe it's easy just to explain. So um, instead of dot product, you can calculate the sum between vectors. And then apply a linear layer with dimensions. The input dimension will be h, and the output dimension will be 1. So in the output, you will get actually just numbers, and then apply softmax. So this is how typically we use attention now. We don't use the dot product, but we apply a linear layer to sum or the product of these vectors. And linear layer returns these numbers, and linear layer has also learnable parameters. So this attention will be also trained. Okay, so we don't have time for recurrent neural networks, so we'll continue next time. But I want to ask just one question. Why don't we use the pre-trained word embeddings? Why I actually create new embeddings, or I said we can initialize these embeddings by pre-trained embeddings, but why don't we use just ready embeddings? Yep.
Is it because it's different in the context of job descriptions versus like natural language?
No. I mean, you're right that it's more general. It doesn't depend on the specific. But do you remember how word embeddings were actually trained in word2vec? They looked at the context, like nearby words. So, but what is which words actually will be in the same position very frequently? Yes, you can just.
Yeah, like anything that means the same, or it's not like a synonym.
But what about not the same? If the same is fine, then they will similar words will be in the same context. But if you think about antonyms, they will be also used very often in the same context. Like this movie was nice, this movie was awful. It will see the same context, and they will have close embeddings. So if you want to classify your text on sentiment analysis, the use of the pre-trained embeddings will be unuseful because you will have opposite meanings will have the same actually embeddings, and you will get the same results in the output. So that's why we actually want to train or fine-tune the pre-trained embeddings. Okay, so yeah, that's it for today. And
Over tomorrow, which sections do you need me for problem solving?